Okay, so when last we left, we had looked at the titration curve for what kind of a titration curve is this? What is in the flask for this titration curve? Is it an acid or a base that is in the flask? Tell your partner. For this titration curve right here, in the flask, is it an acid or a base? Whoa, what happened? Crazy. This should not be difficult. Is it an acid or a base? Acid. Why?
Because it starts at like a lower pH.
Because the pH is low to start. Okay, and what? And so we would be in the burette. We would have the base. And from the shape of this curve, could you tell me if this is a strong acid or a weak acid that is being titrated?
Weak.
It's strong because it does not have a little hill at the beginning. That's one way of checking it out right away. Okay, there's no little hill. So this is going to be a strong acid, and we're titrating it with a strong base. Okay. Now, what if we had this? Is this, what are we starting with in the flask? In the flask, we have a strong base. And in the burette, we have strong acid. Because again, there's no hill. Okay, the hill would go the other way this time. So this is a strong, strong titration. No hill. Therefore, strong, strong. How else could you tell? Even if you couldn't see the hill. Oh, maybe we'll go into that later. We'll talk about that later. Okay? Well, here, I'll bring it back for you. There we go. Okay. Now here, we had just gotten started on this. We had just looked at point number 1, yes? And we'd said we have this little hill. It starts at a higher pH than the acid. So we have one thing that's different, and we have two things that are different. Is there a third thing that you can see here that is different from the strong, strong titration? This here is a weak acid in the flask. I'm sure it says weak acid on the other side, but I'm going to write it here so you can see it. And up here we have a strong base. What else is different? Here, I'll draw you in a little red one what the strong, strong one would look like, the corresponding strong, strong one. It would look like this. Whoops, Make it in red. Well, let's go back to our strong. So this is on page 94. Okay. What can you tell me about the equivalence point? The pH is 7. And that is for a strong titration. How can you recognize the equivalence point? How do you know where the equivalence point is? Like, here it says, it points at it for you and it says equivalence point. But what if I drew this and I said, you circle the equivalence point for me, please? Where would you put the circle? How do you know what volume the equivalence point occurs at? Chat with your neighbor. Or yourself. That sounded pretty good to me. Did you want to say that again a little louder? Oh, except for you've just taken a huge bite of your sandwich. So I'm going to let you off the hook on that one. Anyone else want to tell us where we would find the equivalence point?
In the middle of the vertical line.
In the middle of the vertical line. Okay, so the equivalence point is in the middle of the vertical line. So now you know that you could label the equivalence point for me on a graph if you were asked to do so. And if I said, what volume does it take to get to the equivalence point? You would say 50 milliliters because you're like, oh, the vertical line is at 50 milliliters. And if I said, what is the pH at the equivalence point? You would say, what is the midpoint between here and here? And that is right here. And so that is at pH 7. Okay, so that's a strong titration. Let's go look at our, back to page 96. This is our strong weak titration. What is different? We have that hill at the beginning. It starts higher. What else is different? The equivalence point, the pH is not 7. The pH, is it higher than 7 or is it lower than 7? The pH at the equivalence point for weak strong, for a weak acid, whoops, I should write this. For a weak acid, strong base, pH at the equivalence point is greater than 7. Now, I'd like you to think that through a little bit and think what particles are present at the equivalence point that might be making it basic. And to get you thinking about that, if you're having any trouble with that, I'm going to write a little equation here. Just to make it a bit shorter, I'm going to write HA instead of CH3COOH because it's just shorter. So I have HA plus NaOH, and this is our weak acid, and this is our strong base. I would like you to predict the products of that reaction and figure out whether that is a one-way arrow or a two-way arrow. Once you have written down what you think are the products, check with your neighbor. See if they got the same thing. First of all, one-way arrow or two-way arrow? Or we don't know. Remember, as long as one of the reactants is strong, what happens? It will go to completion. Imagine you have somebody who's really strong pushing that way, right? There's like little weak people over here, and somebody really, really strong is pushing that way. Imagine that I'm over here, and who's somebody who's really strong? I used to know like the really strong people, Arnold Schwarzenegger, but he's like 75 now, so like he's probably not as much anymore. But he's still probably a lot stronger than I am. Do you guys know who Arnold Schwarzenegger is? No, not really. Okay, who's a really strong person? The Rock. The Rock. Okay, pretend that Miss Spence is over here and the Rock is over there, and we're pushing. Which way is it going to go? Are we going to reach an equilibrium, or am I going to get shoved over to that wall? I'm going to get shoved over to that wall, and it doesn't matter if there's somebody else who's weak over here helping the Rock, right? All on his own, he's just going to be like, okay, over there you go by the wall, right? So that's it, okay? So it goes one way. And who are our products? NaA and water. What kind of a compound is NaA? It is a salt and water. How much reactant do we have at the equivalence point? How much reactant? Pardon me? At the equivalence point, what?
Just like salt and water there.
It's just salt and water. How much reactant do we have? None, because it's all completely reacted and there is no excess. So how much reactant at the equivalence point? None. All reacted, no excess. So at the equivalence point, the only thing we have is the salt and the water. So when I ask you, what is present at the equivalence point that is making the solution basic? What is it? The salt and the water. Which one? Is it the salt, or is it the water, or is it both? Now remember, this is in an aqueous solution. So the water that you're making, does it matter? No, because you already have like thousands and millions and bajillions of water molecules. So this water doesn't matter. And besides which, water is what pH? Neutral. Yes? Okay, so who is making it basic? The salt. And I'm going to let you know right now that one of the questions that comes up is, why is the pH of a weak acid, strong base, why is the equivalence point above pH 7? And do you know how many people will answer it? And they'll say, because the acid is weak and the base is strong. Therefore, it's more basic. That is not an answer. That is not why it is. That's not why it's basic. It is basic because you have a salt. And what do salts do that make solutions basic? They hydrolyze. Okay. So we're actually going to go down here because it probably says a lot of this down at point 3. Okay, so anyway, between points 1 and 2, H3O is slowly getting consumed by the OH. Okay, so here we are at point 2. We're just before complete neutralization. And at point 3, here is our equivalence point. So we're talking all about the equivalence point here. So the equivalence point, halfway up the vertical portion of the curve. At this point, the moles of NaOH added equals the moles of CH3COO in the analyte. And so the H3O and the ions are completely neutralized by the OH ions. So this is the actual reaction without an A. We've got the CH3COOH. These are all gone. They are used up. There is none left over. So all we have is the salt. I mean, we've got water, but it's the solvent, so it doesn't really matter. What is the pH at the equivalence point of this titration? Let's go read it off the graph. What is the pH at the equivalence point? What would you say? Don't you ever just want things to move along? Don't you ever get frustrated that everybody just sits there silently? Does it not frustrate you? It would frustrate the hell out of me. I'd be like, oh my God, let's move it along. Frustrates me now. But if I were a student, it would frustrate me too. I'd be like, it's 8.3 or 8.4 or 8.2 or.
Think about it, it's like.
Yeah.
Look at it a little.
Right? Yeah. No, that's fair. That's fair. Okay. So the pH is what? 8 point, what do you want to say?
Let's say 3.
Let's say 3. It could be a 4, it could be a 2, whatever. Okay, we're reading off a graph. It doesn't have to be perfect. But the pH is 8.3, which means that it is basic. What is making it basic?
The salt.
The salt makes the hydrolysis of the salt makes it basic. And in fact, I'm going to get even more specific. It's the hydrolysis of the anion in the salt. Okay. So all we've got at the equivalence point, NaCH3COO. So who are the ions? Oh, sorry, let's write this in here, 8.3. Who are the ions in the salt? Na plus and CH3COO minus. Does Na plus hydrolyze? No. Does CH3COO minus hydrolyze? Yes. And if you don't know, what would you have to do? You would have to look and say the conjugate acid is CH3COOH. And then you go look that up on your table and you say, is it strong or is it weak? So do we get hydrolysis? Yes. So we're going to now write the hydrolysis reaction. CH3COO minus, and remember hydrolysis is the reaction of an ion with water. So don't write the whole thing. Don't write NaCH3COO. The Na as a spectator, get rid of it. Don't want it. So you have the ion and you have water. Who are the products? CH3COOH plus OH minus. So is this a solution acidic, basic, or neutral? It is basic. How do you know that it is basic? Because it made hydroxide. Excellent. Now, what is happening after the equivalence point? What is making the pH so high here? What is making the pH high? The NaOH, because we're adding more NaOH. We're adding NaOH and all the acid is already gone, right? So after the equivalence point, we're adding NaOH, which dissociates completely all the way. And all we have is we have that OH minus ion from the NaOH. Okay. Oh, and look, here we have a comparison between the strong acid, strong base, and the weak acid, strong base. Isn't that nice? Now, I'm just going to take a quick look and see. Never mind. Okay. Okay. We're going to label a part in here. From about here to about here, this region is called the buffer region. And I'd like you to think about why we might call it a buffer region. I want you to think about what you need to make a buffer. You need a weak acid and you need its conjugate base. Look what we have here. We have a weak acid, and if we haven't reacted it all the way, if we haven't gotten to the equivalence point, we will still have weak acid present, yes? And if we're past the initial stage when it's only weak acid, we will have produced some conjugate weak base, yes? So in between the very start and the equivalence point, you're going to have some weak acid, some reactant, and you're going to have some weak base, some product. So halfway between the start and the equivalence point, you will have some reactant and some product. So at this point right here, this is all reactant. And when we get to this point here, this is all product. Yes? Actually, I should probably draw it at the top of the line, but that's okay. What do we have in between? Do we have all reactant? Do we have all product? Or do we have some of each? We have some of each. And if I have some reactant and I have some product, I have a weak acid and its conjugate base, which means that I have what kind of a solution? A buffer solution, okay? We have a weak acid conjugate base combo, which is a buffer. We have an equilibrium that can shift either way. So are we kind of getting that? At the beginning, we have all reactant. At the equivalence point, we have all products. In between there, we have reactant and product, which means we have weak acid and weak base, which means that we have an equilibrium. Yes? It is less susceptible to change than it would be if you didn't have the acid or the base present. It's not particularly, it always bothered me when I was in grade 12 and I did not really understand what was going on because I looked at and I'm like, well, look at that strong acid, strong base. It doesn't change pH very much either, right? And I'm like, well, why isn't that a buffer? And it's because it's just not. Because you couldn't start adding strong acid, like say you were at this point in the titration, yeah? And you started adding strong acid, the pH would drop like a stone. Like you would be going backwards and it would drop. Whereas if you started adding acid to the weak one partway through, you now have enough base that it would absorb that extra acid. You would have enough of the weak base that it would react with that extra acid and keep the pH relatively stable. Okay, it's not that we're particularly excited that, you know, we have this buffer region and that it's doing something important during the titration. All we're saying is that we make a buffer when we're in that part of the titration. Okay, like I said, it's not doing anything special. You're not like, wow, it's a buffer. We're hanging out and buffering, right? It's just that it happens to be a buffer at that point. Yeah? So if you were to do this and you were to maybe just stop your titration halfway, you could be like, I have a buffer solution and I can now use it to do something else where I need a buffered pH. maybe something in biology or whatever, if you wanted to. Okay? Okay. So let's go on then to this picture here. And like I said, I'm not sure if these pictures make it better or if they just make it more confusing. At least yours are in color this year. Most years they're in black and white, and that certainly doesn't help. But at the start, we have all acid. So this is at the start, all acid. At this point right here, whoops, sorry, I'm not doing a very good job of drawing that line. What would we call that point right there at 25 milliliters? That's our half equivalence point. That's our half equivalence point. And at the half equivalence point, you have 1/2 is acid, HA, and 1/2 is been turned into the base, A minus. Can you see that extra hydrogen on here? We got an extra hydrogen on the acid form. The base is missing that extra hydrogen. So at the start, it's all acid. And I suppose I should put in that that is a weak acid. At the half equivalence point, we have half weak acid and half weak base. How about at the equivalence point? What do we have? We have A minus and A minus. Yes, and there's some spectator ions floating around in there. So it's all weak base. So at the start, all weak acid. Halfway, half acid, half conjugate weak base. At the equivalence point, all weak base. After the equivalence point, we still have the weak base, but we have just unadulterated hydroxide ions, and they are just so much more important than the weak base in determining the pH. They overwhelm the weak base. So we have weak base, A minus, and we have OH. The OH minus from NaOH makes the solution very basic. Does our weak acid, or sorry, our weak base help make it a little bit more basic? Yes, but only a tiny amount. Yeah, because after the equivalence point, if we have A minus plus H2O gives HA plus OH minus, the concentration of OH is high. We have a high concentration. Which way does that shift that equilibrium? It shifts it to the left, which means the contribution to OH from the A minus is very small. And if you don't really get that part of it, it's okay, as long as you're just like, I've got OH from the NaOH and it just overwhelms everything, and that's what's causing the high pH. This is the key point. If you understand that bit up above, that's all right, that's good. But the key point is that after the equivalence point, the OH is what's making it very basic, and you can just ignore the weak base at that point, okay? Okay. How are we feeling? Is it okay-ish? Ish? I'm going to nod and you're going to pretend to nod along with me. Okay. Now, what is the, okay. Oh, here's a good question. This is a really, really good question. So what we have right now is we have, let's see what it says. It says we have 0.1 molar acetic acid and 0.1 molar NaOH. Okay? So in the original diagram, we have 0.1 molar CH3COOH. And what volume does it say? It says 50 milliliters. And we titrate it with 0.1 molar NaOH. And it takes 50 milliliters to get to the equivalence point. We can read that off the graph, right? How much does it take to get there? 50 milliliters. Now, what the question is asking is, what if we replaced the acetic acid CH3COOH with 0.1 molar HCl, also 50 milliliters. So we have the same concentration and the same volume. And what they would like to know is what would happen to the amount of base needed to reach the equivalence point. Would it still be 50 milliliters? Would it be greater than 50 milliliters? Or would it be less than 50 milliliters? You know what I think you guys need? I think you need a 5-minute break. And then you could come back and think about it. What do you think? Would you like that? Yes. We're ahead of the other block anyway, so we can do this. Take a little walk around. Just don't make noise in the hallways. Don't walk down by the office. Don't bother anybody in other classes. Otherwise, I'll get in big trouble.
Just gave it. What did they do? Bro, what did they do, bro?
There's bad practice.
I just do that.
Yeah.
We might start on this on Friday, so anybody's. So it's our next unit, and this is the first half of it, so I don't know how far we're gonna get. And so that's just. Okay, and then we'll see what we get.
Is that correct?
What?
At 7.
Mhm. The pH will be at 7, yes, now what happens to volume?
It will. Yeah. It would be the same.
How do you feel about it? Do you feel that it would be lower? Why? less base?
What makes
So you have a specific volume, because it contains a certain number of milligrams. Yes. Because the rock is still pushing out against complete convection, right? So it doesn't matter whether it's weak or strong, it's still going to take the same rules.
Right.
There has to be someone like after the rock was really strong, because like Arnold Schwarzenegger doesn't work too hard. Yeah, so like, you know, these 2 years from now, I might be looking some stuff.
Yeah. Oh yeah, I saw
Like,
that.
does he just massage his scalp?
Right.
So bizarre.
That's really weird.
Rocking your shower. Oh, very creepy. All righty. So we were taking a look at this diagram here, and would it take more NaOH to get to the equivalence point with the strong acid? Would it take the same volume, or would it take less volume? So is it going to take, to get to the equivalence point, is it going to take A, more milliliters of NaOH, B, less milliliters NaOH, or C, same milliliters NaOH? Now remember, we are replacing 50 milliliters of 0.1 molar CH3COOH with 50 milliliters of 0.1 molar HCl. So the only difference between them is that we're replacing the weak acid with a strong acid. The molarity is the same. The milliliters are the same. Is it going to take A, more milliliters, B, less milliliters, or C, the same number of milliliters to get to the equivalence point? Why do you say C? The other one changes the equivalence point? The equivalence point changes. What changes about the equivalence point? It gets lower. So the pH gets lower? Oh. Yes. Okay. So the pH gets lower with the strong acid. Okay. What does it become at the equivalence point? What does the pH at the equivalence point become with the strong acid? The pH becomes 7. Okay. So we've dealt with this part. The pH at the equivalence point becomes 7. So it does lower. That's true. Now, is the equivalence point going to be at the same volume, at a higher volume, or at a lower volume? What's the same about the two acids? The molarity and the volume. If you have molarity and volume, what do you really have? I thought you said it. No?
No,
Okay.
I don't think I did.
Okay. It looked like that. Oh, I know. You have moles. Yeah? You have moles. So molarity and volume are moles. In fact, we could say that we have 0.1 molar and 50 milliliters gives us 5 millimoles of acid. Yes? Okay. We have 0.1 molar and 50 milliliters gives us 5 millimoles of acid. How much NaOH, how many millimoles of NaOH do we need to get to the equivalence point? We have 5 millimoles of acid. Chat with your neighbor about that.
Just a hunch. That's
Having hunches,
not exact at all.
that's what we do. You know what I'm going to do? I'm going to grab another piece of paper here, and I'm going to say we have HA, and we're starting with 5 millimoles, yes? So if you want to grab another piece of paper, you can grab another piece of paper because I'm kind of running out of room on that one and it's getting very messy. When we get to the final, if our final millimoles is the equivalence point, in this case, the equivalence point, is there anything else on this table that we can fill in? At the start, we have none of this and none of this. How much HA should we have at the equivalence point? You've forgotten what the equivalence point is. What is the equivalence point? It's the point where all the acid and all the base have reacted completely and there's no extra of either.
All gone.
All gone. So at the equivalence point, how much HA should we have left? We should have 0 millimoles left, yes? Because we've used it all up. That's the whole point of the equivalence point, is that we've used it all up. How much did we need to use up in order to get from 5 to 0? We needed to use up 5 millimoles. Now, how much NaOH should we have at the equivalence point? How much NaOH should we have at the equivalence point? We should have 0 because it is all gone. Okay, the reactants are all gone at the equivalence point. I'm going to just keep saying it over and over until it stinks in a little bit, okay? So we have 0 millimoles. Now, you know the change in HA was minus 0.5 millimoles. So what is the change in NaOH? We used up 5 millimoles of HA. How much NaOH do we use up? 5 millimoles. Okay. Because they react 1 to 1, right?
So true.
Yeah, so true. I know. And so how much NaOH must we have had to start with? 5 millimoles. Yes? Yes. Now remember, we said we had 5 millimoles of our weak acid. What if I replace this with HCl? Is there anything different? No, there's nothing different. It takes the same moles of NaOH to react with a strong acid as it does with a weak acid. So if we have the same moles, what's the volume of NaOH needed to get to the equivalence point? If originally it was 50 milliliters with the HA, what volume do we need with the HCl? 50 milliliters. It does not change because the same volume contains the same number of moles. Yes? And I can tell that your guys' brains are getting a little fried because if we go back here, where did it go?
Sorry.
No, it's okay. Your brain should be a little fried by this point. There's a lot going on, okay? There's a lot. If you look at this, what volume did it take for our strong and our weak to get to the equivalence point? The same. Look, oh, the vertical regions overlap. Yes? Same volume. If you change the concentration or the volume, you'll change the number of moles, and then the volume of NaOH will need to change to give you a different number of moles as well. Okay?
Okay.
We'll come back to this tomorrow, okay? But in the meantime, I would like you to try where practice exercises. Ooh, I would like you to do number 1. And number 3. I'd like you to do number 1 and 3 and start on the review. Okay? So page 103, 104, number 1 and 3. Because it's a big review. You want to start on it today, as long as you don't have like a test tomorrow or something. I understand if you don't. Number 1 and 3, and start on the review.
As you know, I'm very long forward.
Okay.
Can I
Do it now? Sure.
can I just bring my pencil?
Yeah. You're welcome. See you.
Let me do my speech really quickly. Oh. I think Andy's doing it now.
There we go. ¿Por qué?
I just don't. It's like I'm trying to say, they like killed the first one against them, but it's like where also wait, so I just I don't know. I know. I thought I was gonna do it the next day. I know. Yeah, it's going to happen soon. Okay. I just do wish there was a day where just everything stopped. That worries. I need to stop. I was just like, nothing happened. I lay on the floor, I lay on the couch, I lay on the bed. It was so good. Wait, what? 6 hours of things, right? I don't know how to say no. It's okay. Right, or line. Yeah. That makes sense. Right?
That's
A lot more. Oh, yeah. And I'm so sorry.
There's not people going, oh, I'm not.
That's their money. Yeah.
You're not going to stop you, right? We're not going to slow down.
It's
You all fail.
you all fail. It doesn't matter because they're paying to be there. That makes sense. Yes, thank you.
Hi. When do you think I marked it? When would that have happened? Yeah. Not this one. Let me find it. It's here somewhere. I had a meeting at lunch yesterday and a meeting after school yesterday, and this is what happens when I don't have a chance to sort my papers. It's even worse than usual. Okay, that's great. Yeah. Judy, here we go. There you go. You're welcome.
We don't get the one from like earlier.
We will.
Oh, okay.
Yes.
For this question, is it because I
It's
showed
2 out of
this?
2.
No, because usually in the book it says to show your work is KB equals K.
All you needed was this.
Ah, okay. Because I didn't specify KA, so I
I
thought
don't
we
care.
were-
Doesn't matter. You
Oh.
just do, that's all you needed. I don't know what this was all about. I just ignored it.
I don't think I studied that one. I didn't remember.
It's all good. You nailed it, so it's all good. All right, my friends, listen up to your name. Laura. She went on. Michelle. Jody. Kaya. Isaiah. Ryan. Hannah, you can't look at any of these, okay? All right, Aaron. Ellie. Thank you. Ellie. Kylie. Jenya. Dorsa. Kokolin. Samira. Jiwon. Another Jiwon, no. Not there. Jonathan. Jessica. There you go. Okay, I need. No.